Welcome, big dogs. Today we're going to continue our FEA post-processing series and evaluating joint slip and joint separation. So in the previous videos we've looked at shear tear out and bolt bearing margins of safety, and then also ultimate fastener load margins of safety. Once we're comfortable with our selections for fasteners and our joint thicknesses, we can proceed to this step in evaluating joint separation and joint slip. So let's go ahead and jump into it. So in the previous video, we've actually already evaluated it using a spreadsheet template as shown here. These are the inputs to evaluate joint separation and joint slip. So we have some parameters here we can pull from our CAD model as well as our CAE or FEA software program. So first input is fastener diameter. We can pull that from our CAD program. So if we go in here, the fasteners we're using are right here. So we can go ahead and measure the diameter of this fastener. And as you can see, it's going to be 0.086, which is a number 2 fastener size. So that's what we would put in this row right here, or this cell. Next we have a torque column. So how do you specify torque? Well, you can go to your vendor and get a torque range, but more than likely you're going to have to calculate it. So there's some rules of thumb to do that. So here's a spreadsheet template that does that. Basically it determines the recommended torque range for a fastener. The inputs are provided right here: nominal fastener diameter, threads per inch, ultimate stress, tensile stress of the fastener, and also a torque coefficient. So where do we get these inputs? Well, let's go back into our CAD model. Let's go over to the model tree. Okay, so this is the number for that fastener. This was pulled from McMasterCarr. So we'd go into McMasterCarr and see what type of data they have. You can see here, this is that A286 stainless steel socket head screw, and we can see some inputs. So we got basically the threads per inch, 56 right here, so we can take that. We also have the ultimate tensile strength of 160,000 psi, and then we also have this drawing over here, and it specifies the diameter, so we could have pulled it from McMasterCarr since they have it, which is extremely convenient. So we can get those 3 data points, and I've already put them in here. And then we have a torque coefficient. So this torque coefficient, a good starting point is 0.2, but it's basically determined from experimental data. Typically it depends on the joints you're fastening together, the material they're made of, and also whether your fastener is going to be lubricated or not. So 0.2 is a good starting point, especially for a fastener that's not lubricated. And then we can go ahead and determine basically our tensile stress area of the fastener using these inputs. And then we can determine the preload force that we need. So for the maximum torque, we usually base our torque on 67% of the ultimate strength. So that's a general rule of thumb. If you don't know, or if you're not given data by the vendor, use 67%. So that'll be your preload force, and then we back calculate our maximum torque using this equation. So the inputs are going to be our torque coefficient, our nominal fastener diameter, and then our preload force. So then we determine our value right here of 7 inch-pounds, and then you may need to convert that to inch ounces. So that's a conversion factor. So multiply it by 16 to get it in inch ounces. And then how do we specify our minimum torque on that lower range? We generally take 90% of our maximum torque. That's a rule of thumb to determine our minimum torque. And so if we do that, we get a value of 6 inch-pounds, which turns out to be 98 inch ounces. Of course, these are rounded right here, so don't get confused by that. So we have our torque range between 6 and 7 inch pounds, or 98 and 109 inch ounces. In this case, I'm going to use inch pounds because it's compatible with my calculator over here. So we're going to use the highest torque value of 7 inch pounds. Okay, the next thing, we have a prevailing torque. So if you have a locking feature like a helicoil, there's going to be some resistance or frictional resistance as you torque it down with a torque wrench. So your torque wrench is going to read the sum of these two values. So how do you determine your prevailing torque for a helicoil? So if we go into our model, let's just make sure we have a locking feature. If we look at this, we do. We have a helicoil right here for this number 2 fastener. So now we need to go get a prevailing torque value, which you can pull from the vendor, but if you don't have that data, a good resource is going to be NASM 8846. You can read the details. It's for class 2 inserts, which we're using here. And this is the table you want to look at. So this column right here, this maximum locking torque, is actually the prevailing torque you want to use or put into that cell. So you have basically a table for fine thread series or coarse thread series. In our case, we have coarse thread series right here. This is our bolt size. So our prevailing torque is 1.25, so we take this value and put it in this cell, so 1.25. And then we have our torque coefficient, which we're going to specify as 0.2 as a general starting point. And then we have our axial load carried by the fastener, or constant right here, C, which we determined in a previous video. So this is that spreadsheet that we used to determine that value. So our C value, or our stiffness constant, that we determined is 26.1%. So we take this value and put it into this cell. So 26.1% is what we'd use, and then our coefficient of friction is 0.25. That's just a general rule of thumb, good place to start with. And then we got our safety factors, and then we have our loads that we pull from our FEA program. So if you remember, we pulled out our loads, and these are those loads that we pulled out for the 4 fastener elements in the CAD model. So this is what we got from our Abacus FEA program. So we're looking at element 3, so I copied these values and I put them in these cells right here. And then we have a force multiplier for linear analysis. So in this case, we're looking at a 10G load. So I'm going to multiply those values by 10 since it's a linear analysis. And so we go through, we update our load values, and we've seen this before. So we look at our margins of safety. So for joint separation under these loading conditions, that margin of safety is positive. So this fastener or the joint is not going to separate. And then we look at joint slip. Our margin of safety is positive as well. So we're good. So in this case, our fastener is torque and is adequate enough to prevent the joint members from separating. So the last thing you want to look at is what torque would you want to specify on the drawing. Well, your torque specification is just going to be the sum of your torque and your prevailing torque. So these two values is what you want your technician or your tech to torque it down to, is the sum of those two values. And so if you may need to specify that in inch ounces, so just take that, multiply it by 16. So this is what you'd put on the drawing. So the next thing you want to do is, we have 4 fasteners in this model. You want to look at all 4 fasteners and make sure that the margins of safety are positive. So you would take all these inputs and put them in a row and column format for each fastener. In this case, I have, from my FEA program, I got 6 fastener elements. They're all the same size. If they're not, then you just have to change the parameters up a bit. So put it in row and column format here with all the inputs, my torques, my prevailing torque. I already pre-filled this out. My stiffness constant, and then my FEA program loads, and then you get to the end here and you look at your margins. They're all positive for joint separation, and then you look at your margins for slip. They're all positive. So, and then you have your torque specifications. So that's what you'd get, and this is what you put on the drawing. And so that's it, guys. That's how you do this, man. That's how you evaluate joint slip and joint separation and specify a torque. And of course, if you have random vibration loads, shock loads, you can still evaluate it using this spreadsheet. So I hope you learned something, and I'll see you next time. Adios.